Hello everyone, my name is Ali and I'm the training manager in France that I will be coordinating this webinar. So before we start, I just want to make sure that everyone can hear me. So please, if you can use the hand icon, you can press the raised hand icon to make sure that you can hear me. Yes, I can see Jong, Alessio. Yes, perfect. Please, everyone, can you use the hand icon? It's quite obvious, so you should be able to see it. Once you press on it, I can make sure that you guys can hear me. So many of you can hear me already, so great. Okay, so I think we can start. So welcome to this webinar for Virtual Dynamic titled What's New in VD 2019.2. So basically at the end of this webinar, we will have 2 polls to answer, and this should take only a minute. So don't leave the webinar before answering these 2 polls. And after that, we will have time to answer all the questions that you might have as you go along the webinar. So please, any question that pops up in your head, just write it down in the question sections. And at the end of the webinar, we will take your questions one by one and we will answer it. So I guess that's pretty it. I will give hand now to Mustafa Duyar and Swapnil Shah, the 2 persons that will be actually leading this webinar. Thank you.
Thank you, Ali, for the introduction, and thank you all for joining us today. So we will have 2 parts in this webinar. In the first part, I'll show you some slides that will summarize the new features of Virtual Dynamics 2019.2, and then I'll hand over the words to my colleague Swapnil Shah, who will demonstrate you these new features.
Can you make sure that everyone can see the screen?
Yeah, I think it is. Yeah, I can make sure that people can see it. Yeah.
Okay, great. Okay.
Yeah, thanks, Ali. So we released Virtual Dynamics 2019.2 2 weeks back on 28th of October, and it supports ADAM 2019.2. So the new features and enhancements are summarized on this slide, but these are not limited to that. So there are also lots of minor features. So please take a look at the release notes to see the entire new features and enhancements of this release. The new features include a new bevel and hypoid gear, UDE. So as you should know, UDE is our terminology and ADAM's terminology that stands for user-defined elements. The other feature is lubricant oil model at general contact gear, and we introduced roller bearing catalogs. The major enhancements include, and not limited to, restructuring of the gear menu, gear train wizard enhancements, silent chain and involute sprocket enhancements, as well as estimate of the gear tooth stiffness. So a little words about the new bevel and hypoid gears. We have new UDs to support bevel and hypoid gear modeling, and it is based on the ISO standard 23509. The bevel and hypoid gears can be rigid body with internal or external geometries, which are parametrics, or it can be a flexible body by means of a model neutral file. The flexible body gears also consider the structural dynamics due to the global component stiffness in the dynamic analysis. Here you can see an animation of a sample simulation that you can also see the contact force arrows as well as the contact area between 2 bevel gears. The gear teeth contact force is evaluated through a general contact, which considers detailed gear geometry. And with this new feature, we are able to model differential gears As you may appreciate, we have been putting lots of efforts over the last couple of releases to address more on the driveline side of the things in the automotive. That includes transmissions, gearboxes, as well as now differentials. The other feature is lubricant oil model. So the general contact gear can now include lubricating oil film on the gear surface. On these pictures, you can see the schematic view of different thickness oils, starting at the top 100 micrometers in the red region, and also in the bottom you can see 200 micrometer oil film as a pink region. The user-specified constant offset layer is added while creating the parasolid files, and that represents the oil film. This oil layer is treated as an extra contact range that effectively adds a damping force to the gear tooth, and the contact depends on oil viscosity, the local distance between the meshing teeth surfaces, and also the landing velocity of the contact point. So this added oil film damping model works on top of the available damping model, which now represents the material damping only. In the next slide, I'll show you a couple of animations. So when the oil film thickness is 8 micrometers on the upper gear, so you can see the contact area between the meshing gear teeth as well as the contact force as a vector represented by a red arrow. So please keep in mind this contact area. Now I'll show you another oil film thickness, which is now 50 micrometer on the upper gear. Now you can see a bigger contact area. So this contact area represents the contact between the bottom gear and the oil film on the top gear. In the same sense, if we increase the oil film to 100 micrometers on the upper gear, now we will see a bigger contact area at the lubricating oil, which is almost the entire thickness of the gear teeth. So to summarize these, the contact area grows with increasing oil film layer. So, but this contact area is not the material to material contact, so it is material to oil film contact on the gear teeth surface. We also introduced roller bearing catalogs in this release. So by picking a supplier name and the supplier specific bearing type and name, we populate the required bearing input data fields. So in this release, we include the catalogs of INA and FAG suppliers, and we plan to add other suppliers catalog one by one. So to make the gear menu more intuitive and user-friendly, we have restructured the gear train menu. So now we have two groups. One is gear elements, the other one in gear forces. So in gear elements, as you can see here, the spur and helical gears are separated from bevel and hypoid gears. By selecting those, you can input the parameters related to those gears. The other enhancement is Gear Train Wizard that has been extended to allow the user to specify 4 more gear-specific input data. These are addendum modification coefficient, tip reduction, delta tooth thickness, and the inertia. So if you have been using the Gear Train Wizard so far, it really makes life easier while putting together the complex gear train models for gearboxes, transmissions, or any type of gear train. And with these 4 new input fields, the life is even easier. If we move to involute sprocket enhancements, now it is possible to specify the involute sprocket tip and route in the form of triple arcs, and the triple arc contact calculation has been included. So each sprocket tooth flank can have contact with the chain link on its 3 regions that we differentiate between tip, involute, and the route region. The contact request data names have been shortened and labeled accordingly, that you can see on this slide with different colors. So we can output the data on, for instance, sprocket 2, number 11, which is represented by T11, and the left and the right flank with FL and FR abbreviations. And for each flank, we contain 3 regions, the data for 3 regions over the flank, tip, involute, and the route. The detailed specification of involute sprocket tip and route in the form of triple arcs was possible. However, the contact of this triple arc region was not implemented in the previous release. Now it is included that we can calculate those contact forces, and the contact request data names have been shortened to be able to read it easier. The other enhancement is for involute sprocket. We can now calculate the route bending stress according to an Agamat standard. On this plot, you can see the route bending stress example that you can plot with this capability now. As for the silent chain enhancements, now we have detailed output data for different zones that we call from zone 1 to zone 4. So for each chain link on the left and right, we call zone 1, zone 2, and for the other teeth, zone 3, zone 4. So for each zone, we also calculate the contact points at 3 different locations that we call it track 1, track 2, and track 3. Yeah, this is a sample animation results that you can see the chain dynamics of the silent chain with detailed involute sprocket profile data, as well as the silent chain detailed profile data. And the next is gear tooth stiffness estimation is now possible for the 3D phase, 3-phase gear force, and it is based on the ISO standard 6336. Now, by pressing this estimate button, the stiffness is calculated automatically based on the geometric data that user inputs. So in summary, we released Virtual Dynamics 2019.2 2 weeks back, and it is based on Adams 2019.2, and the new features are, as I already told, number of enhancements for especially gear train and chain drive specific items. So now I'm handing over the words to my colleague Swapnil Shah, who will show you, actually demonstrate you these new features.
Thank you, Mustafa. So the development team has been very active. So I have a lot of things to show you in a very short time. And I will start with the easiest things. I will open a new Virtual Dynamics session. And let's begin with the small enhancements in the gear train wizard. So over here as an add-on, I open my gear train wizard. And of course, I have a pre-prepared property file. I'm just opening a property file from my shared database for an inline-PHY manual transmission. So we load the property file, which will contain all the informations about the shafts, gears, bearings, which you can just prepare and change as you need. So in my case, I have, let's see, for example, 5 shafts. Yeah, each shaft has a particular number of gears and bearings. So my intermediate shaft, which is shaft 2, yes, it will have many gears and a couple of bearings. I can define all of them. So as Mustafa just showed you that now there are even more parameters which you can already define over here, which means you do not have to manually define them. Of course, you have the contact forces, the contacts which can be checked over here, whether they are correctly defined between all your gears. And let's just build the gear train. One of the things which we do not see in this gear train is this automatic estimation of the stiffness and the damping of the gears by the ISO standard 6336. So earlier, all the gear pair used to receive a default stiffness and damping value, but now an estimate based on the ISO standards will be done, which makes life much easier in concept phase. Okay, so we have a gear train over here, and let's build a couple of dynos so that if we want to run the system. And okay, let's have a look at the gear force, this ISO estimate which we were talking about. And while doing that, we can also look at the new gear menu which we have. As per our understanding, more logically divided different things into spur and bevel gears, between gear elements and gear forces, so and shafts, of course. So all of them are much more easier to find. So we will look at one of the 3-phase gear force, which was automatically defined by the gear train wizard. And as you can see over here, the stiffness and damping, because they were already automatically calculated without and not a default value, they're already there. Otherwise, in a gear pair which you create on your own, you can always estimate it yourself. So this was more about the gear force and the estimate which we had. And if we look at our gear train, let us first modify one of the shafts, because of course all the shafts will have some default values. So all of them look same right now. And okay, let's build some bevel gears. So for that, I would need the construction frame. Yeah, and I know where to place my bevel gear. So I'm going to place a bevel gear on reference shaft 3. Yeah, in reference to the shaft output shaft of my gear train. What I'll do is I'll build one more bevel gear, which will be dependent on the construction frame of the bevel gear 1, which makes it easier. These interdependencies are very nice to use because it means that the entire gear train is dependent on a single point and you can move and rotate the entire system together. So I will rotate my second bevel gear by 90 degrees over here. And so now I have my construction frame. I'll make a new bevel gear element. So let's call it bevel 1. I'll take a property file, and again we will attach it to this output shaft from my manual gear train. I'll use the coordinate reference which I just created. Yes, these values are just 0. I do not need them. And of course, they have to be fixed to the output shaft. I'll fix them and I'll create my first bevel gear. Similarly, for if I have a differential, for example, I can create a second bevel gear. And in this case, I have a different property file. And just for an example, let me just put it on a ground. And I will of course use the construction frame which I created for the bevel gear 2. It cannot be fixed on the ground, so it will be revolute. All the properties are there, and I can now create my second bevel gear. And there we see it. So this is our manual transmission with an example differential. And of course, now we will have to build the force. So in virtual dynamics, the gear element and the gear force are always separate. So we will just name it, let's say bevel underscore diff. We just select the two gears with which we want to connect the bevel gears as a contact. And of course, for your force, you will be giving in the stiffness and the force exponent and all the different parameters. I have many things to show you, so I don't want to put in a lot of values right now. And so this was more about the gears. Now, if we look at the bearings, before that, I would want to update my shaft, which was default, as I mentioned earlier. You can have a very varying shaft with a different number of sections, different diameters, different lengths. So this is just an example that I update my shaft. And now that I have my proper shaft, of course, I would also need to update my roller bearings. And this is a good opportunity to have a look at the catalogs, which we have now included in Virtual Dynamics. So I just go to the dialog box of the roller bearings and open a catalog. I can use width, outer diameter, inner diameter to filter the different bearings available from FAG and INA catalogs. This case 25 diameter. And let us just select one of the bearings from the catalog over here. So I just accept the values and it populates my dialog box in the roller bearing dialog box, and I can just accept them and create a new bearing. This is an analytical bearing, so it is a little difficult to see the rolling elements because it's analytical. Maybe let's do one more bearing where we make it geometrical first. So we will replace the analytical bearing with a geometrical bearing, which is a little higher fidelity model. And when I replace it, of course, there will be a default property file which is being used, which might not match my shaft. So I go back to the catalogs. I filter based on my inner diameter. Again, I select a bearing of my choice. Let's select this one. Okay. I again accept it. It updates the properties in my dialog box, and now I can create my new bearing very easily. So there we can see it a little nicer. You have the number of rolling elements. Let's have a radial ball bearing, for example, instead of the cylindrical. The process remains the same, but now from the catalogs of FAG and INA, you will be able to have a different source. Again, I am just selecting a random new ball bearing and updating it. So as Mustafa already mentioned, we are trying to introduce new catalogs in the upcoming features. Yes, so this is how my bearing looks like, but I close the dialog box. But what if I want to, I'll go back. What if I want to create a bearing which is not in this catalogs? So for example, I have found a bearing from the SKF catalog, but these catalogs never have all the information to define the bearing. So I found this particular values from the catalog from SKF very easily. So I put in these values and I say generate values. It will create this outer ring diameters, number of rolling elements, the roller diameter, and all of those things will be estimate based on our assumptions. And again, I can accept these values, and what we will have in the end is actually a bearing from SKF. And there we have the new bearing. I also want to show the oil film thickness. So I'll go to the standard interface where that is applicable. I had a model prepared earlier, which I will use over here. And first of all, I'll go to modify in a gear. So let's say I'm selecting a gear. You always had this option of exporting the geometry from Virtual Dynamics. Now you see a new field which says oil film thickness. So this is 2 micrometers. No, that's maybe too small. Let me increase the oil film thickness to 20 micrometers. Exporting takes a couple of minutes. So actually I had just exported this before the demonstration so that I do not have to wait for a couple of minutes. but the process remains the same. For example, I can export the geometry. Let's say for the second gear, I define a different oil film thickness, just increase it by a factor of 10. So it's 0.2 millimeter, which is 200 micrometers compared to 20. And once you have exported the geometries which I had done earlier, it's very easy to set it up. So I go to the folder where it was exported, and you see the two files where they are differently named. Yeah, the files already had the name of the oil film thickness, and I can import this external geometry very easily. And now instead of my internal geometry, I will have a parasolid external geometry for one of the gears. We would do the same thing for the second gear soon. And what is important to note is that this oil film thickness, which becomes a part of your parasolid model, it is already defined in the naming of the gear. So let's just look at the second. I will import. As you can see, you have two different files with different oil film thickness OFT values. And let me import the other one. My dialog box, yes, it's here. And there it is. So now once it is done, I will have an entire gear pair with two external geometries with the oil film already defined in the CAD model. So if we try to look closer to this gear pair, which is now parasolid geometries, we are talking about 20 and 200 micrometers. It's not very easy to see, but maybe you are able to notice that the distance between the two CAD, the two gears, is very less because of the increased oil film thickness, which is already present. So how does this oil film thickness come into consideration? So I think that's the smart part. We will have to, of course, replace our three-phase gear force, which we had as standard, with the general contact where this new oil film theory will be applicable. And as you see in this general contact gear, of course, you have the contact stiffness and the force exponent. Over here also you can use the new estimate button, right? And it is good to see that the two different oil film thickness which I had defined, which was there in the naming of the files, it is already recognized by this contact over here, which means that, and of course, not to forget that you have the calculated option also available, which automatically calculates the stiffness. It's a variable stiffness, and you can of course always press F1 and go to the dialog box. To, like everything else in virtual dynamics, you can go to the dialog box, and for example, this oil film theory which has been applied in this case, you can of course go to all the details to understand the theory and the physics behind it. It is important to understand that this contact oil film force is slightly different than the oil film force or the oil film theory which we had defined for the three-phase gear force. And this pressing F1 and going to the dialog box or going to the virtual dynamics help is universal. So everything which we saw today, the bevel gears, the shaft, the roller bearings, the catalogs, how they work, you can always just press F1 in any of the dialog box and come to the help and try to understand all the different parameters that are available. So Mustafa, I think that is all I can show in this short period of time.
Okay, thank you very much, Swapnil. Now, actually, what we can do is we can move to the question and answer session. So if you have any questions, please just go to the questions part of the webinar tool and type in your questions. You can also see on the slide our contact details, our website address and support email address, virtualdynamics@fev.com. So if you come up with some other questions later on, you can always contact us.
Okay. Thank you, Mustafa and Swapnil, for this great presentation. So while waiting for the anyone who wants to ask a question to write it down, I will just launch the two polls. And this should take like a few seconds for everyone to answer. Okay, I think we're good for this one. I will jump for the second question. So do you receive release announcement emails? Please select one, yes or no. Okay, so I think we're good. I'm gonna close it. So I think we can start with the first question. So the first one is, why didn't we replace the bevel beer with the external geometry before having general contact force?
I'll take this one. That's a very, very good question and very good observation, I must say, because it is true that till now, all the spur and helical gears, the general contact was valid only with external geometries. The bevel gears, which is a completely new UDE, we put in a lot of efforts such that the general contact force, which is also used in the bevel gears, same as the spur and helical gears, it is now also applicable with internal geometry. This makes life much easier. We have already done some studies, for example, to use this general contact force in bevel gears using internal geometry and external geometry, and the results are almost identical, which is good. And now we are also planning to put in efforts to actually have the same advantage in spur and helical gears, so that you can use this general contact force without having to use external geometry every time. I hope this answers the question.
Okay, thank you, Swapnil. I have a second one. So how to get the values of bevel gear contact?
Yeah, I think this is because I did not fill in all the values. I would say this was an oversight. We are already working on it, that in future, when a customer or whenever a user generates a bevel gear force, then all the values will be automatically filled in. Basically, the dialog box will be populated. In this case, of course, the software cannot really give values for every different gear. But if any user wants the default values, you can always just open the template or the assembly available in the shared engine database, and you can have a look at what are the default values which we use as the start values for our calculation. But of course, then those are only the start values. You might have to adapt these values based on the material or your type of gear or the gear sizes.
Okay. There's a third one that we might have answered maybe during the webinar, is, do you plan to add other roller bearing catalogs?
Yeah, I slightly touch on this point during the webinar. Actually, yes, we do plan to include other bearing catalogs, and possibly the next one will be SKF, and hopefully we are going to make it available in the next release, which is planned for April next year. And there will be others coming up step by step.
Okay.
And of course, sorry interrupting, but of course you should not forget that we have this custom So if anyone is using roller bearings and they come across catalogs from any of the suppliers, you will see that you have half the or some basic information available for all the different bearings. And that's why we also introduced this custom roller bearing module, where you give in this half the information, and the other information like the number of rolling elements and the ring diameters will be estimated for you, which is helpful if the catalog which you want to use is not available.
Yeah.
Okay. I have a final question remaining. So, is only the stiffness estimated, or also the damping for the three-phase gear force?
So in the three-phase gear force, the damping is also estimated, and this is also based on, let's say it is based on the mixture. The stiffness is based completely on the ISO standards. If you look at the ISO 6336, for damping, there is some room for your own imagination, let us say. But we actually talked to some experts in the field who use these ISO standards and our own FEV expertise. And based on that, we are estimating, in combination with the ISO 6336, the damping in the gear contact also.
Okay. I think that's it. Thank you guys. Thank you for this informative webinar, and for everyone who have attended. I hope we'll see you all again in our next webinar.
Yeah. Thank you all for your participation and your interest. Yeah, I should repeat. So if you have any further questions that come to your mind later on, you can always contact us.
Thank you, everyone.
Thank you. Bye.
Bye.
Bye.